Hey guys, and welcome to another video on the channel. In today's video we're going to be taking a look at the proof for L'Hopital's rule, or a proof I came across which I found actually pretty interesting, so I was just going to share it with you guys. So let's say we had this case here. So let's say we had the limit as x goes to 2 of x squared minus 4 over x minus 2. Okay, now if you're new to limits, you're probably not sure how we would evaluate this, but if you have done limits before, this is a pretty easy question. So a limit basically means we are going to approach this value for this given variable here. So here we want to figure out, alright, as we get closer to 2, what does this turn into? Now the problem that arises here is pretty much if we were to substitute in 2, so usually if you evaluate a limit and it's simple enough, you just plug in the value you're approaching. So if we were to plug in 2 into here, what we're going to get pretty much is, alright, 2 squared minus 4 over 2 minus 2. So basically you have 4 minus 4 over 2 minus 2, which effectively is 0 divided by 0, which is undefined. We can't evaluate that, okay? Now, there's two ways we can work out this particular limit, okay? So the first one, we could factorize it, okay? So here we could rewrite this, so the limit as x goes to 2, we could rewrite the so x squared minus 4 can be written as x plus 2 times by x minus 2. Because if you were to expand this, it would give you the following results here, okay? So x times x is x squared, x times negative 2 is negative 2x, same here, positive 2x, and then minus 4, and that gives you x squared minus 4, okay? So here this can be factorized, let's just get rid of this now. This can be factorized into x plus 2 and x minus 2. Now here, because we factorize that, we can clearly see that these guys are in common, meaning you can cancel them out. So what we're left with is the limit as x goes to 2 over x plus 2. Now here we can just plug in 2, so what we get is just 2 plus 2, so we get the limit is 4, okay? Another way to do it is L'Hopital's rule. Now L'Hopital's rule basically means as the limit as x approaches a of, let's say, f of x over g of x, that is the same as just f dash of a over g dash of a, okay? So basically the derivative of the top function and the bottom function at that particular point you're trying to find the limit of. Let's test it with this example here and then we'll look at the proof. So the derivative of x squared minus 4 is just going to be 2x. So you have 2x over, and the derivative of this is just 1, okay? So this is my f dash of a and this is my g dash of a. Now in this case here, a is what we're approaching, so it's 2. So what we have is just 2 times by 2 over 1, which gives you 2, okay? So we got, oh, sorry, not 2, 4. I think that's the worst mistake I've ever made. Alright, 4, and we get the same thing, okay? Let's look why this is true. So first of all, the case when we're trying to work this out is, so if we have the limit when, let's say, x is approaching a, you're going to have f of x over g of x. So when it approaches a, you're going to get a case we have 0 over 0, okay? Therefore, this implies that f of a is equal to 0 and g of a is equal to 0, okay? Now this is fine, we can work with this, okay? So what we can do is we can rewrite this like this. So the limit as x goes to a, now because 0 is technically nothing, what we can do is technically do this. So because that's equal to 0, what we can do is just go, alright, f of x minus 0 and g of x minus 0. We haven't changed anything at all between these two lines here. They're still the same, okay? What we're going to do is replace this with that, because it is 0 at that point there, and replace this with that, okay? So we get the limit as x goes to a of f of x minus f of a over g of x minus g of a, okay? Because that's how we've defined it. Now, we can do anything we want to this expression as long as we apply it to the top and bottom. So effectively times this by 1, it doesn't change anything. Now we can make 1 equal to anything. So what I'm going to do is I'm going to make 1 equal to 1 over x minus a over 1 over x minus a. And I'll show you why I did this. Now this is valid because I have the same thing being divided by itself, so it's equal to 1. We're going to replace this into here. So effectively we have the limit as x goes to a of f of x minus f of a over g of x minus g of a times by, and I'm just going to write this thing here. I'm just going to copy it. I'm going to be a bit lazy. This here. Okay? Now, top times top and bottom times bottom. Okay? So this will turn into f of x minus f of a over x minus a over g of x minus g of a over x minus a. And there's still a limit in front of this. Now, what we can do here is we can technically apply the limit to the top and the bottom of this. So let's just do that. So we'll apply the limit to the top and to the bottom. So we can rewrite this entire thing like this. So if I copy that, move it there, I'll effectively this here and this here on the denominator and the numerator. Okay? Now this is the definition of f dash of a, pretty much, because here this is the first principles. Okay? So if you remember from the first principles, you have the limit as h goes to 0 of f of x plus h minus f of x over h, pretty much. This is the exact same setup, except we're plugging in a certain point. So this is the derivative of f at the value of a. So this is equivalent to f dash of a. And likewise here, this is just g dash of a. Okay? Now we said this was equal to our expression above. So that means that the limit as x approaches a of f of x divided by g of x is equal to f dash of x when it's equal to a over g dash of x when it's equal to a. And that's L'Hopital's rule proven, pretty much. Okay? We've got an example here and we've got the proof here. Okay? Again, this is an interesting proof to go over. Obviously, it's probably a bit more complex than that if you went into real analysis over it, but overall, I think it's a pretty clever proof. Okay? Let me know you enjoyed the video, like and subscribe, and I'll see you in the next one.